Thanks for tuning in. My name is Mark Claypool. I'm a professor of computer science at Worcester Polytechnic Institute. It's an engineering school near Boston in the US. Did this work with Ed, Tian, Zajay, and Xiaokun and their students. And we're looking at latency compensation and cloud-based game streaming, supported by Google, who are makers of the Stadia system. So traditionally, you take your game console and you have it in your living room or your computer room or whatever you have at home, where as a player, you're sitting down, you provide input, the game console renders it, displays it on the screen, you then react. Nice tight loop. You might have local latency from the system, but other than that, it works pretty well. Emerging technology are these cloud-based game systems. And there's a whole bunch of vendors that are building them, including Stadia, but also Amazon, Microsoft, NVIDIA, and Sony. And the idea is you take your game console that was in your living room and you push it out into the cloud. And so now this is doing all the heavy lifting. It's doing all the game computation, the physics, the rendering, and so on. But you still want to get all that to the player. So the player over here no longer has this sort of full fat client. It has this thin client where you provide input in your living room. And all that input, though, has to go up across the network to the cloud server where it gets processed. Now the frames aren't displayed, but they're rendered as video and they're streamed down to the client. And so there's lots of advantages to this. There's a few disadvantages. Happy to chat about after the talk or during the break sometime. But in particular, one major disadvantage you can think of is that there's now new latency. So here we only had local latency. Now every action has to go through this round trip time from the client to the server. Now, traditional games have dealt with latency for a while, traditional multiplayer network games. And in fact, they have this whole set of techniques called latency compensation techniques. They're designed to overcome latency. And this is a taxonomy we're developing, and that's another talk for another day. And I'll go through that, but there's a whole bunch of techniques that have been established that would help with latency. And these are all for traditional games for the most part. So games where you have this fat client, but we already know that we can't do a whole lot of that kind of stuff because this client is thin in the cloud-based game system. It can't do processing. So there's a whole bunch of these techniques that don't work. So companies like Google and other providers are looking for new ways of compensating for latency. Now, this paper that I'm going to talk about today, we're talking about a technique called attribute scaling. So it's a new technique. So attribute scaling inspiration stems from this idea of flow. If you're a game designer, you've probably heard of this. The idea is that you have sort of two major axes. You have difficulty and skill. And the idea is that a game designer has an experience in mind, sort of this vision where the game is going to be fun. And as the player gets better, the game gets more challenging so that it's still a challenge to play and it keeps that funness. So that's the idea here. So as the player gets better, as they get higher in the skill axis, the game itself gets more difficult. With the idea that there's sort of this sweet spot, this flow, where if you can keep the game designed in that space, the player will sort of be maximally immersive on the most fun. And it's not a strict linear relationship. It's kind of fuzzy, it wanders through here. But if it gets too hard, that can be frustrating over here. If it's too easy, that can be boring. So the idea is to keep it in that zone, in that sweet spot. So what happens when we have latency, when we have delay, you take what could have been a perfect experience for the player, you've now made it more difficult. So the player's not happy. So put it another way, if you kind of take a look at this space where this is game difficulty on this axis, and you got fun on that axis, again, there's a sweet spot, just right. So that's where the game is maximally fun. It's the most fun it is. And that's, again, often for a developer, they've developed it for that game console in the living room and they've tuned it, and it's lots of testing, play testing, and there it is. That's the best place to be, right? But so if you get the game too easy, no fun either, but they've gotten it here. But if you have lag, now we're talking about the game being too hard. So the fun has gone down. So what we can do is we can try and adjust the game difficulty. So do that on the fly so that we can tune it so that we move them up the curve so they're back to where the game is more fun. Okay, so that's the idea. Game's more difficult with latency. So let's see if we can adjust the game to kind of keep the performance in that flow, in that sweet spot, players in the zone. So here's attribute scaling applied to a simple game, Flappy Bird. And so we'll call it Flappy Bird. So the idea is Flappy Bird, if you don't know it, simple enough to describe. You have kind of one button you hit, you try and have a bird fly left to right, where these obstacles, these pipes, you can see it in this picture, kind of are coming at the player. You have to time your flaps just to make it through the pipe. And so the idea, again, you've tuned it and everything's good so that you flap and make it and flap. You're playing in, you make it for a little while and you listen, whatever, you've tuned the game that way. But now when you're playing this in a cloud-based game streaming system and you have this extra latency, what happens is you go to tap the button at just the right spot and that latency causes it to be harder to do. And in fact, what happens, it makes it harder to hit. So now the challenge has gotten harder and it's no fun, it's too frustrating. So what we can do is we can do attribute scaling, and we actually can change the game world. So in this case, you can sort of see in the far right picture where you've taken those pipes and you've spread them apart a little bit further. You made it a little bit easier for the player to actually flap and make it through that gap when there's latency. So we can do that live, real time. That's the idea. Right. So Flappy Bird's simple. You might say, oh yeah, there we go. Even a simple game like Flappy Birds has lots of attributes that can be scaled. So we're talking about the gap between the pipes, but you could also change how the separation, because that changes the difficulty also. You can change the pipe width. You can scale attributes about the bird, gravity, maybe jump velocity, speed. So even a simple game like Flappy Bird has lots of attributes to scale. So it's a rich space that game designers can tweak in order to keep the game fun. And the idea is hopefully we can do those tweaks, adjustments live based on latency. So how to adjust those? Well, probably the adjustments depends upon lots of stuff. What game you're playing. I talked about Flappy Bird, but in practice, it probably has to do with attributes about the game actions. And these are some attributes that have been proposed by other researchers. Check my paper for references, but precision, that's how precise the action is. Deadline, how soon does it get enacted? How important is the action? That's the impact. Can you predict what's going to happen? What is the rate? So how rapidly do you have to actually provide input? These have all been proposed as ways that actions are impacted based on latency. Sorry, latency affects the impact of how these actions are impacted by latency. So what we're doing in this paper is, first of all, can I go ahead and take an action and see if I can scale it? Does it work? So can I assess player performance with latency and with different amounts of scaling? If so, can I model it? Can I generalize the use of that attribute scaling method so that game designers can do it? Right, so how are we gonna do that? This is our methodology. So we're gonna develop some games that have a scaling action in place. We're gonna conduct a user study to see if we can understand if this attribute scaling is working, and if so, we can hopefully generalize it. The generalization will be in the form of a model. So the model is going to provide scaling. We're going to evaluate it in a game, take that model, stick it in the game, see if it makes the game more fun with latency. We'd like to generalize that. So that means pushing it into a game engine and then deploy it in the real system and evaluate it. Right, that's the bigger vision. This paper talks about these first three steps. That's the towards in the title of the paper. So we're working towards this. We have sort of these first three steps. So develop some games, conduct a user study, see if we can model that attribute scaling and suggest how we might use it. So we have two games. The students have designed two pretty fun games, Catalyst and Nova. Catalyst is a 3 versus 3 multiplayer capture the flag game. So where players are first person looking through the eyes of the player. They have a bunch of projectile spells they can cast, kind of like shooting. Some are defensive, some are offensive, different kinds of things. They work as a team to get flag and get points in combat. The other game we've developed is Nova. Nova is a single player game, and it's a rhythm shooter. So it's a rhythm game, if you know Guitar Hero, where you have music, and when the music plays notes, you kind of provide your input with the notes. Here, there's these asteroids that are coming to hit the player's ship, and you have to shoot them within the window. So as the beat goes boom, you shoot at the same time. So you're in the zone, clicking on notes and trying to hit it as the music's playing and avoid destruction by the asteroids. All right, so two games, both of them play tested, super fun. We had lots of people play them. They're cool. Graphics, everything's custom, designed by the game designers to tweak and balance and that kind of thing. Can we make them more playable with latency? So we have to come up with attribute scaling, and there's two different ways we've done this. Catalyst is going to scale the hitboxes. So the idea is that if I'm shooting at an opponent with a spell, and if I tune it so that, it's a kind of, there's the box, I can hit them, that's scale 1.0. What I'd like to do is make a version of it that's easier to hit if there's latency. And so let's try a scale 1.5. But here we've scaled the hitbox to be 1.5 times bigger, and then twice as big on that side. So here the hitboxes are shown for edification only. They're invisible. So the models are the same. It's just that your spells will hit in a bigger target area if you're casting them. So Catalyst is using this as an attribute scaling hitbox size. Nova is using something a bit different. Nova has, again, remember this temporal idea, where you have this time window that you have to hit the note in, hit the asteroid in that coincides with the note. And if you miss it, then that means the asteroid is going to hit you. So that's this temporal window. So we can scale that. So kind of the base scaling of 1.0, we can make the scale, that window time-wise can be longer and even longer. So we can scale that with 3 ways too. Right. So Nova uses a temporal scaling technique. So what our approach is to user study, where we're going to vary a whole bunch of parameters and we're going to see how users do. So, can we control things? Does this technique work for these 2 scaling techniques in these 2 games? So we're going to vary latencies, of course. So we have 4 different latencies we're going to look at, from no latency, kind of a local system, to 125 milliseconds. That's kind of the upper end of what most cloud game providers are looking for. So we have this full range of network latencies that are sort of our cloud-based game systems. We're going to look at different scaling values. So those one sort of standard up to twice as big. Again, you often imagine a game designer knob is how hard is the game. Remember, we wanted to keep them in the flow. So we'll look at difficulty. So if you make the game easy versus hard for Catalyst, that has to do with how fast the opponents are moving, so their speed. If you're looking at Nova, we're talking about how many beats are spawning per second. So how much, the music is flying around, or it's relatively simple. Okay, so these are the parameters that we're going to vary. We're going to all combinations of each, get users to play it, observe how they're doing. So the users come in, give us a survey. Let's get some demographics. They play one game first, shuffled. They're going to play both games. For each game, they're going to practice a bit so they know how to play. Then they're going to play a round of the game with a certain lag, certain latency, play it for like a minute. Then we're going to shuffle the settings. So they're going to have a different latency, difficulty, and scaling, because again, we're going to look at combinations of those and repeat. So they do that over and over again for all combinations of every parameter we're changing. They actually do each 3 times. So in about a 30-minute period. And then the idea is we're going to look at the results. So we had 23 users that participated in our study. We wanted 30 or more. We did this during the pandemic, like lots of research nowadays, and a little tricky to get people to participate. But again, we're happy with this number, 23. From our university is our population. Our sample is drawn from there. So mostly university age, mostly males. Our university is mostly males, but we had 6 females also. And they're mostly gamers. They play on average 10 hours per week. These are some sort of core demographics. So not enough to slice it up further by different groups, but sort of a reasonable size sample to explore our approach. So we first are going to look at accuracy. So Catalyst accuracy is, again, shots hit over shots fired. Nova accuracy is the notes hit also, and it's actually over total notes that are spawned. So you could say that's the notes that come in. How many of those do you hit? So we're going to try and model accuracy, because again, this is how the player is doing. How's the player performing? So this is a graph showing both games. Here's the results. The x-axis is latency. So we have 4 different latencies. No latency added up to 125 milliseconds of latency added. And then this is Catalyst, is the top graph. So we're looking at accuracy. So how accurate is the player? So this is Catalyst and this is Nova. Both have accuracy, slightly different measures, but they both have accuracy. The data is shown with box and whiskers plots, where box and whiskers goes, the bottom of the box is the first quartile, Q1, top of the box is the third quartile, middle line is the median. We have a mean dot there for each. And then those whiskers go to the largest non-outlier for each side. So you can look, first of all, there's lots of variation. The spread of the boxes towards you, how much do players vary? And again, people vary from game to game, so that's not too surprising. Even players, they don't play consistently over the game. There's lots of variation. So we're looking for sort of trends. And you can see that there is a downward trend, certainly in the mean values. That's for Catalyst. Likewise, there's a downward trend in Nova, sort of a range. So as you added latency, the game apparently did get harder, at least the player performed worse with latency. We also have data on the scaling. So does scaling make it so that the accuracy can go up? And again, these are our scaling values. Again, with Catalyst, we're scaling the hitbox size, 1, 1.5, and 2. With Nova, we're changing that temporal window. So again, 1, 1.5, and 2. We're looking at the effect on accuracy. Again, same box and whiskers here. And so again, the upward trend, you can sort of observe it. So as you are scaling using a scale factor, we're getting a larger, a higher accuracy for Catalyst and a higher accuracy for Nova. So scaling seems to let us have a knob to counteract maybe the performance degradation from latency. The other knob we might want is for the game designer is difficulty. So we have, again, we've tested 2 difficulties. The speed of the avatar is for Catalyst at the top. Note spawn rate for Catalyst on the, for Nova on the bottom. Again, box and whiskers. And sure enough, we have this knob that lets the game designer, if they change the difficulty, we can hopefully adjust the settings of the game also based on that knob for each. Okay, we did some statistical tests, see if those values are statistically significant. So for each game, is latency, scaling, and difficulty, are those statistically significant for the parameters we set? And p-values look good kind of for both, suggesting that as we change latency, as we change scaling, as we change difficulty, sure enough, that has the intended impact to accuracy in terms of predictions. Okay, so it seems promising. So next step is, so let's model that. So what are we modeling exactly? Well, can I predict accuracy? So for Catalyst, given a given latency, given a scale value, and given a difficulty of the game, can I predict what the accuracy would be? Right, that's this equation. Nice and simple, add them linearly. These are the coefficients. Each millisecond of latency decreases accuracy by 0.08. That's how you read that, for example. The scale factor increases by 20 for each number, and likewise difficulty. So those are, you could put meaning into the coefficients if you want. But either way, we can predict accuracy with R squared of 0.95. So pretty strong for Catalyst. Nova, here's the equation for Nova. Again, different constants, different scaling method, different game. R squared isn't quite as good, but still maybe reasonable. So suggests we can use data to predict the accuracy for each game. We have a model for each. Now, the accuracy wouldn't be what the game designer would use. And what you're really doing is, what we want to do is let the game designer say, hey, I want them to have this experience, right? I want to be in this flow zone. And if they have a latency, that's where I want to scale it. So we actually want to flip these around and adjust it to scale. So Catalyst would say, can I compute what the scale should be? So the game designer says, I want 80% of my shots to hit whatever the right tune is. I mean, that's how difficult they want to make the game. The system itself is going to measure the latency. So what is the latency from the client to the server? And then the difficulty is baked into that current level, whatever you're playing. And so using this equation, the system on the fly would automatically scale and Catalyst the hitbox. Similarly, we could do the same thing for Nova, of course, different parameters and so on, and we can scale the temporal window. So as the player is playing, if a player has a lot of lag, it would scale their temporal window accordingly. If the level got harder, because the game was getting harder, you could scale it accordingly and so on. So you would adjust the scale to fit the current situation in the game and in the player's networking. Okay, so this illustrates how it might work for Nova, just as one example. So the game designer might want, I want about 80% accuracy, because that's the right challenge. You don't want to be too easy, not too hard. That's in that flow zone. So they would tune it that way, 80%. And so that'd be the right scale. They'd figure that out. And then as the player might have latency, so as the player is playing the game, a certain player might have 55 milliseconds of latency. So it would scale, their experience appropriately. If they had more latency, it would scale it even more. And if they had, 125 milliseconds of latency, it would scale it even more. So it would scale the experience. So instead of the player having this degraded experience, they would actually have a constant experience in what the latency was in terms of their performance. So that's how we'd use it. And that brings me to the sort of the end of this paper, and I'll talk about next steps. So to rehash, cloud-based game streaming is coming. It's actually here. If you haven't tried it yet, go try it. This paper is talking about a new latency compensation technique that we're trying to develop for such systems called attribute scaling. And the first couple steps, we've built some games, we've tested our parameters, we've derived models. And the idea is, what do we know? Well, actually does vary. So player performance varies with latency, scaling, and difficulty. And more than just varies, we actually can use that to build models of player performance, which will let us adjust scaling automatically. And so the models work really well for Catalyst and Nova, and they let us pick scaling values that will keep performance at about the same rate. So next steps, of course, is actually, we've done those first three. Let's try it out in a game. So we have the model, looks promising, try it out in a game. So take the full game, live latency, have the players play it, see how it works. But we want to do more than that. Rather than having it in game code, which we can do, in fact, we know we can, we're going to take that same model and stick it down into the engine. So the game designer can go ahead and make use of it, just saying, hey, engine, scale my hitboxes, for example. So we're doing that in Unreal Engine, so we can push that in Unreal Engine. You can deploy that. Stadia lets you deploy Unreal Engine games, so we deploy that with Stadia, and then now we have a live system, and then we're going to evaluate it. So that's where we're going. I'd like to acknowledge students that built Catalyst: Alejandra, Joseph, Cameron, Adam, and James. So crackerjack set of students that did that. equally talented set of students, Michael, Nina, and Alex. They built Nova. It's awesome. The Google Stadia team has been awesome in supporting this work and getting us stuff to be able to deploy this in Stadia. Brian, Doris, Elizabeth, and Philip. So thank you for your attention, and hopefully I'll have time to answer any questions.